want to do question number 2 here for sure, and I'm thinking maybe question number 3. Are we good with doing those two? Yes? All right. Let's take a look at number 2 first. It says an arrow is fired horizontally with a speed of 25 meters per second from the top of a 150-meter tall cliff. Assuming no air resistance, what's the distance that the arrow will drop in 2.5 seconds? So here's the cliff. Okay, the height of the cliff is 150 meters. It's launched. This arrow is launched at a velocity of 25.0 meters per second horizontally. It's going to follow. What's the shape of that path again? Yep. Good. It's going to follow a parabola. Now, listen very carefully here. It says, how far does it fall in 2.5 seconds? They're telling us that we're looking for the vertical displacement. Don't we already have it? Aren't we already given the vertical displacement here, 150 meters? Right. The 150 meters here is irrelevant. We're told the height of the cliff is 150 meters. The height of the cliff could be 6,000 meters. That would be a high cliff. But it could be 6,000 meters. And in the end, this arrow would still fall the same distance in 2.5 seconds. The height of the cliff is irrelevant. So I'm going to erase this. Okay, the height of the cliff is 150, but I want to know how far it falls. It's not the total height of the cliff. It doesn't reach the ground, at least not necessarily. I just want to know how far it fell, maybe how close to the ground it got. All right, that's all we have, I think. Break it up into x and y components because we got it. There's two components of motion here, x and y, and they're independent of each other, so we can't do them together. We have to treat them separately here. The x component will always be described, Leandro, by this equation, right? V is equal to delta d over delta t. Why? Why? Why can we always group 1 there, Grace?
There's no acceleration.
Good. It's a constant velocity, no acceleration, so it's got to be a group A problem, and there's only one equation within group A. All right, my group, or my y component is going to use group B. Specifically, we're going to try this one first, VIT plus 1/2 AT squared. Why group B for the y component? Yep. Yeah, gravity is acting vertically, not horizontally, but there's a force of gravity pulling it down, causing it to speed up as it falls downwards. All right, let's plug some numbers in here. Horizontal velocity, 25 meters per second. Displacement, we don't know. Time, hey, look, we got that. 2.50 seconds. When we solve for delta t here, delta d works out to be 62.5 meters. But that's not what the answer sheet says. What did I do wrong? What have I done wrong? Caitlin? Yeah. I've just solved for the x component of the displacement. It is absolutely correct for the x component of the displacement. But the problem is, that's not what I'm asked to find. I'm asked to find the y component of the displacement. So what I've just found there, if you did this the same as I did, don't worry about that. You don't need to do it. But if you've done it, it's not a big deal. Take us what, 30, 45 seconds? Okay, I know that's 30 or 45 seconds of your life that you are never getting back. But you've got a long life ahead of you, so another 30, 35 seconds out of your life isn't the biggest deal in the world. Listen, if you recognize right away that you don't need to do the x component here, great. Save yourself that 30 seconds. But if you don't, so what? Do it anyways. And then you realize, oh, I didn't need to do that. Let's go to the y component. The y displacement is what we're looking for. VI is what? 0. The time is 2.5 seconds, so we're going to say 1/2 of -9.81 times 2.5 squared. Do the math there, and it should work out to be negative 30.7 meters. Hey, why did I get negative and they give me a positive for our answer here? Yeah, we actually solve for the displacement, right? And the displacement ends up being downwards, so it's going to be a negative value. What do they ask me for? Not the displacement. The distance. And distance is a scalar, right? So technically, The answer is not negative 30.7. It's positive 30.7. But I certainly wouldn't take marks off if you said negative 30.7, because that's the displacement. You just weren't asked to find displacement. Is that good? So look what I could have done. Not even touch the x component. I didn't even need the 25 meters per second. That's the problem. If you use that like I did, that's okay. If you recognize this right away, more power to you. Save yourself that 30 or 45 seconds. All right, let's take a look at question number 3 now. It says, what's the horizontal speed of an object if it lands 40 meters away from the base of a 100-meter tall cliff? There's a high cliff. We're going to make the object a ball. I don't know what it really is, but... And we're looking for its horizontal speed. We know that it lands 40 meters away from the base of the cliff here. So it's going to look something like this, right? And we know that we're going to do the x and the y components. And we know that we're going to use what equation to solve for the x component? Olivia? What equation for the x component? Good. Got it, because it's a constant velocity horizontally. And for the y component, or what equation am I going to use? Good. We're going to use one of my group B equations, probably this one. Start with that one. If it doesn't work, then try something else. Okay, let's plug some numbers in. We don't know what Vx is. That's what we're trying to find. Delta D, we do know this time. 40 meters divided by T, don't know it. Delta D for the y component is negative 100 because it ends up being 100 below where it started. Vi for the y component, 0. So that means 0 times time is 0. Half of negative 9.1 is negative 4.905. Take it over by dividing. And negative 100 divided by, it's going to be about 20, I'm going to say about 4.5-ish for the time. Who's got that? 4.515 seconds, which we're going to plug back into here. When we do that, we should get 8.86 meters. Can anybody explain to me? I asked this question on Friday, but I'll ask it again. Why is this velocity and this velocity different? Why is this displacement and this displacement different? Why is this time and this time not different? Why are those times the same for our x and our y, but our displacement and our velocities are not the same? And our acceleration, for that matter, isn't the same either. Else? Times is scalar, and the rest of them are vectors. Vectors, x or y. Scalar, it's both, right? Guys feel comfortable with that? Okay. This question, your next example, 211, says, baseball players often practice their swing in a batting cage in which a pitching machine delivers the ball. The baseball is launched with an initial velocity of 22 meters per second at 30 degrees. This one's different. And the player hits it at the same height from which it's launched. So in other words, we don't know what height it was launched from. We don't know what height it's hit at, but we know it's the same height. It's hit at the same height as it's launched. And that's a pretty good approximation. Okay, you're hitting a ball in baseball. Okay, your arms, if you're a pitcher, are at a certain height when they release the ball. The batter's arms are at more or less the same height when they hit the ball. So the ball ends up at about the same height above the ground as it started. It's a projectile motion question, almost like the ones we just did. But there's one thing here that maybe we want to spot first before we do the x and y components, before we do the group A and group B. Dom, what is it? It's got degrees in it. We see a funny angle there, right? And what do we say to funny angles? We look at it straight in the eyes and say, I don't like you, funny angle. So we get rid of it. To get rid of it, we draw it off to the side up here. We're going to say cosine 30 degrees is equal to adjacent over hypotenuse. The side of the room is going to find that one. And we're going to say sine 30 degrees is equal to opposite over hypotenuse. This side of the room is going to find that one. 19.05, thank you. And this one's going to be 11, right? Okay. Got my little aside done. Now I'm going to go x and y components. Okay, I'm going to start now just like I did with the other one. Remember, I've told you, you will see one of these as question number 1 on your final exam. Of course, you're going to see it on your unit test on Thursday as well. It will either be on your exam a question where the ball was launched horizontally, okay, like off the top of a building, or launched at an angle like this. If it's launched at an angle, get rid of the funny angle, then go to x and y components. If it's launched horizontally, then just go straight to your x and y components. By the way, I could have, if I had have chosen to, erased this, right? Gotten rid of that, and then just said, look, this is 19.05, and this is 11. That means the horizontal velocity is what? What's your picture? The horizontal velocity is what? Yep. Go ahead, Zach. 19.05. We don't know what delta D is. That's what we're trying. Yeah, we don't know what delta D is. We're not trying to find that. I was thinking we were. We're solving for T. How long is it in the air for? We don't know it either. The y component of the displacement, what do you think that is? In this case. It's not always that, but it is in this case. Picture this. The ball is thrown from this level over here. It's thrown, it goes up like this as a parabola, comes down like this, and is hit at this level. How does the initial height compare to the final height there? Zach? They're the same. So then what does that mean about the displacement vertically, if the initial height and final height are the same? 0. It wasn't 0 before, right? It was negative something, negative height of the building. Now it's 0 because the ball is landing at the same height as it started. Didn't happen before. Okay, VI for the y component is 11. We don't know what time is. Oh, this is looking a little ugly. Let's simplify this just a little bit before we actually solve it. A half of negative 9.81 is negative 4.905. But we still have t, although it's only one variable, it's in two places. How do we solve for that t? No, we don't actually need to use the quadratic formula for this. If displacement wasn't 0, we'd have to use the quadratic formula. But since some of you have never even seen that before, I can promise you'll never get a question where you have to use the quadratic formula. This one's easier, actually, than the quadratic formula. Is it legitimate to say add 100 to both sides? Sure it is, if I do it to both sides. Is it legitimate to multiply every term by 16,142? Sure it is, as long as I multiply every term by 16,142. Is it legitimate to divide every term by 21,694,912? Sure, as long as I divide every term by that. Is it legitimate to divide every term by t? Sure it is, if I divide every term by t. What's 0 divided by t? 0. What's t divided by t? 1. So 11 times 1. What's t squared divided by t? T. Oh, now it's looking better, right? Now t is only in one place. I got that by dividing every term by t. Only worked because delta d was 0. Chi, if delta d wasn't 0, I couldn't have done that. I would have had to use the quadratic equation there. Let's divide 11 by 4.905. It's going to be equal to 2.3-ish. 2.24 seconds, which we're going to turn around and plug back into here now. Actually, no, that's what we're looking for, isn't it? For how long is the baseball in the air for? Yeah, done. 2.24 seconds. What if we had been asked for how far does it travel? Oh, we could have put it back into here and solved for delta d for the x component, right? We just weren't asked to find that. Once again, did the x component matter? No. Does it matter that you've just used, really, does it matter that you've just invested 30 seconds of your life into that? Getting the x component? Not really. Not really. Is that okay? Okay, I got 2 more questions for you to do here. The first one you're going to see is real similar to the homework questions that you've had. A little bit trickier, maybe. Question number 2 is similar to, not exactly the same, but similar to the example we just did. Question C, that's the star that we'll put on that one. That's the challenging one. Okay, that's what I haven't showed you how to do yet. But I want to see, without showing you, if anybody can figure it out, and then we'll definitely go over this to show you how to do it if you can't figure it out. All right? So questions 1 and 2 will give you some time to work on that now. Now let's take a look at number 2. So the ball was thrown with a velocity of 20 meters per second at 30 degrees, travels for 3 seconds before it strikes the ground. Listen, it doesn't say that this is launched from ground level. It doesn't say that it ends up at the same height that it started at. Okay, the example that we did looked like this. But this question doesn't say that. Okay, we're saying we're launching at 30 degrees, 20 meters per second, and maybe it goes down here. Okay, maybe it ends up right here. We don't know. Okay, we don't know. We're going to draw the picture down here, but we don't really know until we actually solve it what happens to it. We know that the time of travel is 3.0 seconds. We also know that we have a funny angle here that we don't like, because we don't like funny angles, period. So we got to go off to the side here and do the x and the y component of that 20 meters per second. When you use cosine sine, I'm going to assume that you can do that. X is equal to 17.32 meters per second, and y is equal to 10 meters per second. If we want to, we don't have to, but if we want to, we can replace that with this. 17.32 to the left, and 10 meters per second upward. All right, now let's do our x and our y components. For x, we're going to say d over t, like we always do, like we will on our unit test, like we will for question number 1 on our final exam. V equals d over t. For the y component, same thing as we always do. VIT plus 1/2 AT squared, although we do have a few more options there for the y component. Plug in some numbers. Do we know what V is for the x component? Kai, what is it? Good, 17.32. Do we know what D is for the x component? Mitchell, do we know what D is for the x component there? How far it travels horizontally? That's what we're looking for, isn't it? We don't know what D is. Do we know what T is? 3 seconds, right? So we can actually solve for delta D for the x component here right now. It's 51.9 or something like that. Going to round to 52 meters. Okay, done. A is done. We didn't even need to do the y component for A. If all you're asked for in the question is the horizontal displacement, you're done. You don't need to bother going to the y component. But we are asked for more, the height from which it was thrown. We're going to solve for delta D here, for the y component. VI is, VI for the y component, Caitlin, is what? Good, 10. The time here is given to us as 3 seconds. In the example question, it wasn't, right? We had to solve for it. This time it is. Okay, so what I want you to do is calculate the first number, 30. Half times negative 9.81 is 4.905. 3 squared is 9. So that's going to work out to be 5 times 9, 45. It's somewhere around negative 14, I guess, right? According to the answer, I guess. Now, what have we just really solved for? Not the height, but something real close to the height. So what have I actually solved for there? Yeah, the displacement. Now, we're looking for the height, which is a scalar. It's like a distance, right? So technically, the height would be 14 when the displacement was negative 14. But if you leave it as negative 14, I'd still mark that right. Okay, either one, 14 or negative 14 there. The maximum height of the ball. Anybody get this? Yes, Sam? Good. Good. How'd you do it, Sam? Oh, okay. How'd you do C? If you did it before B.
I didn't figure out B without using C, so with C, I originally wanted to calculate just the distance before it got past 10
Yeah. Yep. Okay, for the y component. Okay, so I'm going to write that down as a separate color here. VF squared is equal to VI squared plus 2AD. That's what I'd use too, by the way. So far so good. You're on the same track as I would have done.
Okay. Once you have that, doing that ends up doing.
Oh, but hold on. VI is 10, right? Okay, what's VF? Good. That's the crux of it right there. Okay, that's the crux of it right there. Horizontally, it keeps going at a constant speed, Zach, forever and ever and ever, right? Horizontally, constant speed forever and ever and ever until it hits the ground. But vertically, it slows down, and when it reaches its peak height, it stops vertically. So that means if we're analyzing the y component, that means VF would be 0. VI would be still 10 squared plus 2 times negative 9.81 times the displacement. Now, when you solve that, take that over to the other side. We get I think it's 5.1 it works out to be. That's a positive, actually. But that's not my answer. It's close, like you're really close to being there, but it's not quite the answer. What do you got to do with that?
Once you have, well, you can add that to the distance that it responds from.
Good. So what we're saying here is that Sam just found this. We already had this. The height from which it was launched, right? So if we add the 5.1 to the 14 meters, that gives us the maximum height, right? The maximum height is 5.1 meters above where it started. And then, well, You got to add to it the height from which it started, the 14 meters. Does that make sense? Don't ever analyze the x component when you're trying to find maximum height. Why would you? Maximum height is vertical. Whenever you're finding maximum height, always do it the way that Sam did it. The f squared is equal to the I squared plus 2AD. The good news is, Sam, most times you get a question, you're not going to have to add the 14 meters to it. The number you get will be your final answer. But just with the way this question is set up, it doesn't work out that way. Is that okay? All right, I'm going to give you a worksheet right now. There's two sides to that worksheet. I want you to start on side one. Side one involves problems like this. Side two involves problems like this. I want you to work on both sides, but I want you to do this one first. Got it? We'll see how far we can get there during class today, and then we'll see what we assign for homework for tomorrow, okay?